Today we're tackling, well, one of the universe's absolute biggest head-scratchers. It's a discovery that really turned our understanding of, well, everything on its head. We are talking about dark energy, that super mysterious force that seems to be making the universe expand faster and faster. And our mission today is to cut through the jargon, and give you a clear picture of why some fascinating new hints that its power might actually be changing, have scientists buzzing about the ultimate fate of the cosmos. Okay, so let's start at the beginning. Back in 1998, right, there was this huge discovery. Researchers, they looked at maybe 50 or so exploding stars, supernovae, and found something completely unexpected. The universe wasn't slowing down like everyone thought. It wasn't even coasting. Nope, it was speeding up, expanding faster and faster, which immediately gave rise to this idea of dark energy, this sort of unknown fuel driving the acceleration. It was such a big deal it won a Nobel Prize. Like throwing a ball up and have it just accelerate away from you, just wild.
Exactly, and how they figured that out is pretty neat, actually. It all came down to mapping and measuring light from these specific explosions called Type Ia supernovae. These happen when a certain kind of star, a white dwarf, explodes. And the key thing is, they're incredibly useful as standard candles.
Standard candles, right. Like knowing how bright a light bulb really is lets you judge its distance.
Precisely. These supernovae have a predictable peak brightness. So by seeing how dim they appear to us, we can gauge how far away they are. Then you look at their redshift. That's how much their light has been stretched towards the red end of the spectrum because space itself is expanding. By combining distance and redshift, they saw the farther away supernovae were moving away faster than expected. That pointed to acceleration.
Okay, got it. So that was the initial shock. Now, fast forward. Scientists wanted a clearer picture, right? More data.
Definitely. And that leads us to this new compilation, Union 3. It's the largest standardized data set of these Type Ia supernovae ever put together. We're talking over 2,000 supernovae gathered from like 24 different experiments.
So it solves that comparing apples and oranges problem you get when you mash together data from different telescopes to different methods.
That's a huge part of it, yes. The way Union 3 works is they carefully analyze the light curve for each supernova. That's how its brightness flares up and then fades away. That helps figure out its true intrinsic brightness. Then they adjust everything, calibrate it all onto the same scale.
Must have been tricky dealing with data from so many sources.
Oh, absolutely. The biggest challenge is probably dealing with all the tiny uncertainties. Like maybe a telescope's filter changed slightly over years of observation. They use this really sophisticated statistical method. It's called a Bayesian hierarchical model. Basically, it's a smart way to combine all this varied data while properly tracking all those different potential errors and uncertainties. It makes the final result much more robust. And this data set, it lets us look back maybe 7 billion years into the universe's history. Pretty deep.
Okay, and here's where it gets really interesting from what I gather. The analysis of this huge Union 3 data set, it hints that dark energy might not be constant, might be, evolving, getting weaker over time.
That's the tentative suggestion, yeah. And it's a big deal because our standard model of cosmology, the one that's worked incredibly well for decades, it's called lambda CDM.
Lambda for dark energy, CDM for cold dark matter.
Exactly. That model assumes lambda, the dark energy component, is a cosmological constant. Its strength doesn't change, ever. So if these hints are right, if dark energy is changing, well, that throws a wrench in the works.
What kind of wrench? What does it mean if it's weakening?
Well, it fundamentally changes the question of the universe's ultimate fate. David Rubin, one of the lead researchers on Union 3, put it nicely. He asked, does the universe expand forever or eventually stall or even start contracting again? If dark energy is weakening, then maybe the expansion won't go on forever. It could slow down, maybe even stop, or reverse into a big crunch billions of years from now. Huge implications.
Wow, okay. And this isn't just coming from Union 3 in isolation, is it? I heard other projects are seeing similar weirdness.
That's what makes it particularly intriguing. It's not just one data set showing this slight tension. Other big surveys like the Dark Energy Spectroscopic Instrument or DSI, which uses a totally different technique.
What does DSI do again?
DSI maps the large-scale structure of the universe using something called baryon acoustic oscillations, or BAO. Think of them as like fossil sound waves from the very early universe imprinted on how galaxies cluster together. DSI looks much further back in time than the supernovae typically do. And their early results also show some, let's call it, moderate disagreement with the simple constant dark energy model.
So two different methods looking at different eras, both hinting at the same thing.
Kind of, yeah. Now, As Saul Perlmutter, one of the original Nobel winners, pointed out, nobody's, jumping up and down, rewriting the textbooks just yet. It's still tentative. But having two independent lines of evidence showing a similar, slight departure from lambda CDM, that definitely makes scientists sit up and pay attention. And we're expecting a flood of new data soon. Projects like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope will find tens, maybe hundreds of thousands more supernovae. That should really help clarify things.
Okay, so wrapping this up, what's the big takeaway here? It seems like dark energy, the stuff that makes up nearly 70% of the universe. Maybe it's not as simple or as static as we thought.
That's the core of it. We've built this incredibly successful model based on the idea of a constant dark energy. But if that fundamental assumption is even slightly off, if this cosmic engine driving the expansion is actually changing gears over billions of years,
then our whole understanding of the universe's past, present, and especially its future needs a rethink.
it really does. It raises this profound question. If the dominant force in the cosmos is evolving, how does that reshape our picture of where everything is headed? It's quite humbling, isn't it?
Definitely. So maybe the final thought for everyone listening is this. Just imagine how understanding this elusive, maybe changing force could completely redefine not just the universe's ultimate destiny, but maybe even our own sense of place within it all.